Hello, my name is Sawyer West, and today we will cover formal logic. Before we begin, I want to thank those who gave constructive criticism in the editing phase of the video. My parents, Amelia and Dave West, a friend from college, Nick Anderson, and a professor from college, Michael Staver. Thank you for your help. It is greatly appreciated. Logic is the study of arguments and validity. It is a powerful abstract tool to structure thoughts. Using logic is like baking a cake. We start with the assumptions, which are the ingredients. Then we provide a logical argument, our recipe, to reach a conclusion, the cake. Nobody knows why logic works because the foundation of logic is a system of assumptions about relations defined by natural laws. You cannot prove assumptions within a system derived from those assumptions. In other words, logic makes intuitive sense and it works, so just roll with it. Logic is useful because logic is the foundation of all academic subjects, like mathematics, science, and technology. These are useful to solve problems. Ergo, logic is useful. In this video, we will cover the topics in the book Logic by Stan Baronet, and we will use the notation from the Book of Proof by Richard Hammock. The order I will cover these topics will not necessarily be the same as the order covered in the books. If you enjoy this video and you would like to see more content in the future, please consider liking, subscribing, and turning on notifications. Before we begin, remember to prepare a cup of tea. When talking to someone about anything, how do we know what they are describing? We refer to the definition of their subject, a definition which can come in many forms. An intensional definition specifies some properties that the object has. An extensional definition specifies every object the definition references. A lexiconal definition is the official definition accepted by definition authorities. Stipulative definitions are arbitrary and specific. For example, a slang word defined in terms of another slang word. When a definition is imprecise, we may need to clarify the definition with a precise definition. An operational definition specifies what the object is used for and how to use it. A functional definition defines the purpose of the object. And finally, an ostensive definition gives an example of what the definition is referring to. Statements are true or false statements, and inferences are networks of statements. Inferences must have a conclusion, and premises can be opinions. Words like therefore, thus, so, and hence imply a conclusion, while words like because, since, given, that, and assuming that imply a premise. Explanations accept a conclusion is true and explain, while inferences justify a conclusion is true by arguing why. When we evaluate statements, we see if its information is true and what it implies. Consider the statement, I can explain the subject simply. It is up to the viewer to evaluate the truth of that statement. For the sake of this example, assume the information is true. What can we infer? By Einstein's quote, we may ascertain that I understand the subject well enough. Is this a sound inference? Our assumption that I explained logic simply may be wrong. It is also possible some topics do not lend themselves well to simple explanations, and thus it may not be necessary to explain logic simply to show an understanding of it. Assuming Newton's quote, we should heed the advice of Einstein. This example is becoming too meta, so let's shift our attention to a different inference. Albert Einstein was born on March 14th, 1879, and Isaac Newton was born on April 27th, 1643. Therefore, Newton was born before Einstein. Observe the conclusion is true because it correctly relates the two premises. However, true premises in a conclusion do not guarantee an argument is void of logical component errors. Take, for example, the following invalid inference. The Taj Mahal was finished before Newton's theory of gravity was published, and Peter the Great died before the Stamp Act. Therefore, Newton's theory of gravity was published before Peter the Great died. While all three of these statements are true, the argument is unsound because the relation the conclusion draws between the premises is not guaranteed within the context of the inferences. Valid inferences guarantee the conclusion without a shadow of a doubt by deductive reasoning. When premises are not certainly true or false, we cannot make a valid inference. However, with inductive reasoning, we can make an inference with a probability of truth. There are different types of inductive inferences. Analogical inferences reason similar subjects may have similar qualities. Statistical inferences leverage probability to weigh a conclusion. And causal inferences utilize knowledge of cause and effect. Inferences can be strong, moderate, or weak, depending on the probability they imply the conclusion. When we say an inference is strong, we mean that it has at least a 90% chance of being true. Likewise, a moderate inference has more than a 50% chance and less than a 90% chance of being true. Finally, a weak inference has at most a 50% chance of being true. Note these cutoffs are arbitrary, but useful. Cogent arguments are not weak and have true premises, while not cogent arguments are either weak or have false premises. Suppose you are a child in 1971. You want a golden ticket, and there are only 5 tickets. You stipulate that you will find a golden ticket. How likely is it you will receive this ticket given a bar of chocolate? We can write a function which takes in production quantity and spits out a probability. Sadly, while engaging in research for this function, you discovered there were no Wonka chocolate bars produced in 1971. With this, we should adjust our expectations of winning a ticket. Enthymemes are inferences with missing information. For example, if I say, I own Shrek on DVD, and thus I am never bored, it is assumed that I find Shrek entertaining, the DVD is functional, I have time to watch Shrek, and a whole host of other missing informations. There are 2 types of fallacies. Formal fallacies consider the structure of the inference, and informal fallacies consider every other type of logical error. We will cover informal fallacies first, then discuss logical structure. When the meaning of a term is changed, we call this a fallacy of ambiguity. An evocation prescribes 2 different definitions to the same word. An amphibole is an ambiguity caused from misleading grammar or syntax. When the property of an individual object is mistakenly thought to be a property of a greater whole, this is a fallacy of composition. Similarly, when the property of a class of objects is mistakenly thought to be a property of each of its elements, this is a fallacy of division. In a fallacy of emphasis, the intention of a statement is distorted. Taking a statement out of context to argue against a weaker form of the original inference is called a straw man fallacy. Finally, when one ignores all preceding arguments and diverts the discussion, a red herring fallacy has occurred. Fallacies of unwarranted assumptions occur whenever the truth of a statement is assumed without basis. Begging the question occurs when you assume that the conclusion is true and use that to justify the conclusion. A complex question is when one question contains multiple different questions. A hasty generalization are generalizations based upon a few instances. The biased sample fallacy occurs when a non-representative sample is surveyed to model the results of a census of an entire population. A hasty application of a generalization are the edge cases of where a generalization ceases to apply. A claim exhibits fake precision whenever it presents statistically insignificant information as significant. Relating two unrelated events which happen at the same time is called coincidence. Post hoc is an observation of a pattern made after the fact. When the cause of an event is misattributed to different events with the same cause, we have succumbed to the fallacy of a common cause. When an inductive argument is treated as a deductive argument, this is the fallacy of a slippery slope. When a premise is used to support an unrelated conclusion, there is a fallacy of relevance. Ad hominem occurs whenever the person who proposed an inference is put into question rather than their claim. Tu quo quo is a form of ad hominem where the presenter is accused of hypocrisy. Propositions which solely rely on emotion for support suffer from the appeal to emotion fallacy. One emotion that can be appealed to is an appeal to an emotion of pity. Additionally, someone can concede in an argument because they are threatened with violence. Inferences from ignorance occur whenever someone claims a statement is true because it has not been proven false, or vice versa. Inferences may be sound, but if the conclusion stated is not related to the inference, the fallacy of an irrelevant conclusion has occurred. Finally, whenever someone relies upon the opinion of those who do not understand what they are talking about, they are appealing to an inappropriate authority. Let's consider the logical structure of statements. To the right, we see a chart of Godzilla sizes over the years. By representing the different Godzillas as letters, and representing the statement is taller than with a caret symbol, we can describe the relation between the heights of the different Godzillas more compactly and analytically as objects. Logical quantifiers are descriptors used when asserting a relationship between symbolic representations of ideas. We use categorical statements, written with logical quantifiers and symbolic representations, to describe relationships between classes, sets of objects which share common characteristics. Venn diagrams are used to illustrate these relations. The color green shows the set is non-empty. The color red shows the set is empty, and the color yellow represents that we don't know if the set is empty or not. Universal affirmation statements assert all S are P, and are defined as follows. For all elements S of S, S is an element of P. We see this Venn diagram that if there are S, then S are P, and thus there do not exist S that are not P. Observe that the universal affirmation does not state that P is non-empty. Universal negation statements assert no S are P and are defined as follows. For all elements S of S, S is not an element of P. Particular affirmation statements assert some S are P and are defined as follows. There exists an element S of S such that S is an element of P. Particular negative statements assert some S are not P and are defined as follows. There exists an element S of S such that S is not an element of P. Ordinary statements can be translated into categorical statements. For example, the statement Monty Python's Holy Grail is counted as a great film translates to the categorical statement some Monty Python films, for example the Holy Grail, are great films. Syllogisms are inferences with exactly two premises and a conclusion. Categorical syllogisms are inferences constructed from categorical statements. For example, all vegans are ravers and all Shrek fans are ravers. We can deduce all of the aforementioned groups are ravers. The square of opposition is used to illustrate contradicting categorical statements. Observe if all S are P is true, then some S are not P must necessarily be false, and vice versa. A similar relationship holds for no S are P and some S are P. Statements quantified in normal form do not have negations applied to their entire scope. When considering a statement not in normal form, we can translate these statements into normal form using the square of opposition. Each quantifier has a scope. Variables described by the quantifier within this scope are called bound. If instead these variables were outside of the scope of the quantifier, they would be called unbound. When using quantification in proofs, there are 4 types of quantification and 1 method of disproof. Consider a set which has a quality which holds for all objects in the set. Now choose an arbitrary element from that set. Universal instantiation states that the element chosen has that quality. Consider an arbitrary element of a set that has a quality. Since the object is an arbitrary element, a universal generalization states all objects in the set have this quality. Consider a set which contains at least one object that has a specific quality. An existential instantiation considers that a specific element. Consider an object with a specific quality. If that object is an element of a set, an existential generalization states there exists an element in that set with that quality. To show a quantification is invalid for your nth attempt, use n objects from said quantification to show a contradiction. Truth tables are used to determine the validity of a statement by accounting for all possible truth values of the premises. We may want to describe how close 2 statements are to each other. If 2 statements have the same truth table, they are equivalent. If it is possible for 2 statements to be true at the same time, then they are consistent. When a statement is not consistent, then it is inconsistent. Finally, statements are contradictory when they have exactly the opposite truth value in their truth tables. We have seen so far contingent statements, statements whose validity depends on its premises. There is a second category of statements called non-contingent statements, whose validity does not depend on its premises. Tautologies are always true and contradictions are always false. When the conclusion of an inference is a tautology, then we say the inference is technically valid. In an inference, we often use logical operations to describe a relation between statements. Operators are defined by truth tables that consider all possible truth values of each statement. We can visualize operators with Venn diagrams. The negation operator flips the truth value of the statement. For example, if there is a giant obstruction on the road, you cannot drive. However, if there is not a giant obstruction on the road, you can drive. A disjunction is true only when either of the 2 statements are true. For example, if you are driving and come across a fork in the road, then if either of the roads are unobstructed, you can proceed driving forward. A conjugation is true only when both premises are true. Suppose you and your friend are driving on two different roads that merge into one road. If either one of these roads are blocked before the merger, you and your friend cannot meet. A conditional statement is false only when the condition is met, but the consequence does not follow. For example, suppose after you meet up with your friend, you both become too inebriated to operate a motor vehicle. Consider the statement: if you drive while inebriated, then your car will crash. Observe if you don't drive your car, the statement is never invalidated. Moreover, if you drive and crash, the statement remains true. However, if you are driving and by some miracle you do not crash, the statement is falsified. Before we move on, I want to make it crystal clear that you should not attempt to drive while inebriated. Find a sober chauffeur. Sometimes an inference is in the form of a question. This is called a rhetorical inference. Rhetorical conditionals and rhetorical disjunctions are used to imply an inference. When considering sufficient and necessary conditions, we can visualize their properties using Venn diagrams. A condition that is sufficient implies the conclusion is true. If a conclusion that is necessary is not met, the conclusion cannot be true. Conditional inferences have premises that are conditional statements. If we know information about the antecedent, then we will know information about the conclusion, and vice versa. For example, if we know P implies Q is true, and we know P is true, then Q is true. Alternatively, if P implies Q is true and Q is false, then we know P is false. You can confirm this is a valid inference with truth tables. On the contrary, if we know Q is true or P is false, then we cannot conclude any additional information from P implies Q. There are grammatical rules for these logical operators. Conjunctions, disjunctions, and conditionals must always compare two statements. However, the negation symbol can never be used to compare two statements. Negation can only be applied to a single statement. In the case of ambiguous statements, we use parentheses to specify order of operations. The last logical operator in the line of operations is called the main logical operation. To find the truth value for complex truth functional statements, we determine the value of pieces of the inference in order of operations. The value of the pieces are then used to determine the value of the whole. We can use truth tables to determine if an inference is valid. However, if we attempt to fill out the entire truth table, we would run into computational complexity problems with too many premises. This is because for P premises, there are 2 to the P rows of our truth table. If we suppose the conclusion is false, and we determine all premises can be valid at the same time without a contradiction, the inference is invalid. This allows us to construct a new operation called a biconditional statement, which is true only when either both of the premises are true or neither of the premises are true. We define biconditionals as P implies Q and Q implies P. Consider the intentionally confusing statement: if this inference does not make sense, then it makes sense. Observe if we suppose the inference does not make sense, we see then the inference is false. However, if we suppose the inference makes sense, the inference is true. To prove an inference is valid, we use inferences we know are valid as premises. Then we deduce with rules of inferences and rules of equivalence the conclusion to show the inference is valid. Rules of inferences and equivalence are transformations we have proven valid with truth tables or with previously proven rules. It is left as an exercise to the viewer to verify with truth tables each rule of inference and equivalence. Addition states if P is true, then P or Q is true. Conjugation states if P is true and Q is true, then P and Q is true. Modus ponens asserts that if P implies Q and P is true, then Q is true. Modus tollens asserts that if P implies Q and Q is false, then P is false. A disjunctive syllogism is when P or Q is true and Q is false, thus P is true. A hypothetical syllogism is when P implies Q and Q implies R is true, thus P implies R is true. A constructive dilemma is when A implies B and C implies D is true. Furthermore, if we independently know A or C is true, then we can validly conclude that B or D is true. Finally, a simplification means that if P and Q is true, we know P is true. There are some useful strategies for using rules of inference. Each asserts different rules of inferences can be considered for use. Substitution sets are also useful in proofs. When two statements are logically equivalent, you can substitute one for the other in a proof. Associativity states that when considering a chain of OR operations, or a chain of AND operations, the order in which we consider these operations does not matter. For example, A and B and C is equivalent to A and B and C. Double negation states that if P is true, then not P is also true. Commutativity is when two statements are swapped in position. For example, P and Q is equivalent to Q and P. Both the AND the OR operators are commutative. De Morgan's laws are also important when negating AND and OR statements. Not P or Q is equivalent to not P and not Q. Not P and Q is equivalent to not P or not Q. Distribution applies an operator over multiple statements. For example, P or Q and R is equivalent to P or Q and P or R. The transposition of a conditional statement, also known in mathematics as the contrapositive, is a logically equivalent conditional statement where the premise and conclusion are swapped and negated. Conditional statements can be defined in terms of OR and negation via material implication. When the conclusion of a conditional is a conditional statement, we say the global premise and the conclusion's premise implies the conclusion's conclusion. A biconditional statement is defined as the addition of a conditional statement and its converse. Recall, a biconditional statement is true if and only if the premise and the conclusion are either both true or both false. A tautology is a statement which is true regardless of the truth of its premises. When deducing a new conditional statement, we may be able to find a proof of this statement with the rules of inference and equivalence. However, we can also assume the premise and use the rules of inference and equivalence to prove the conclusion, thus proving a conditional statement. Indirect proofs, also known as proofs by contradiction in mathematics, assume the statement you are trying to prove is false and shows this leads to a contradiction within the statements you already know are true. Throughout this video, I cited a lot of different images which I did not create myself, and these many pages of links are to those images' original source. Thank you for watching. I hope you learned something.